Hello, my name is Ferran Castell. We're going to go a bit into deep dive, and hopefully we're going to give you a bit of an overview understanding of what the technology does and how does it do. What is Ondat? Ondat has an engine, and this engine is a software-defined storage platform for production-grade containerized applications. We install with an operator in Kubernetes. That operator deploys different components, but mainly a daemon set. So we install one pod per host. That is very important because we are enabling developers and people that don't necessarily understand about infrastructure to deploy their infrastructure components as applications. So there is no need to know much about how the underlying technology works to start using it. So once we have this installed, we aggregate all the host capacity, so the disk on those hosts, and we take that into a pool of capacity. So in the end, what we're doing is we are virtualizing disks to use the capacity on the hosts and provide an application-centric, I would say self-service managed storage system to be able to provide production-grade functionality for the storage underlying the applications. So what is inside that container, that daemon set pod that we are running? Well, we have the control plane and the data plane. The control plane, you can think of that as the brains, the orchestrator, data orchestrator. So is where we define some data services, such placement. We have smart algorithms of placement that can decide where is the best place to put data on. We allow scalability through the capacity to create more nodes. So horizontally scale your cluster to enable to give you the capacity to have more and more volumes, more and more nodes. So once all this application is installed, we create a mesh. And that mesh connects node to node and allows us to flow data across these different hosts. That is the storage engine. So we're implementing an end-to-end storage platform, not only data placement, not only scalability, but also the capacity to control every single input-output operation that happens to disk. In that level, we can control things like replication, the compression, or encryption, because we can control every single bit of data that goes to disk. On top of that, we have full integration with Kubernetes. So the main component communicates to Kubernetes, but it's more than that. We want a kube-native solution that is self-service and it self-heals. So what we implemented is not only the operator, but also different small controllers that are capable to enhance the Kubernetes functionality and sync data, sync objects in between Kubernetes and Ondat. So in this way, the user doesn't have the need to understand one thing or the other because it sees a smooth transition in between technologies. From a user point of view, where everything starts is with the persistent volume claim. Persistent volume claim is a definition, no more than that. And on that, we'll take that definition and we'll do under the hood everything that is required to give the capacity to the application to have a disk, a virtual disk. So we can see that an application, or whether it's a pod and stateful set, or even deployments in some occasions, we can just use this persistent volume claim. We have an application-centric model. Now, where does Kubernetes start? Where does it finish? Where is Ondat? Where do we see? So when we install with the operator, we create a CRD that defines a cluster, and everything else is handled for us. So Ondat communicates with Kubernetes when a volume is provisioned, and internally, we will allocate all the resources needed in the host to provide this virtual volume for the container. Now, how does that look like in terms of the data services, or in terms of where we place data and how we place data? Well, we have taken those nodes that are, for instance, our workers in Kubernetes, and we're using them to use commodity hardware to treat them as a disk array, for instance. So what we're going to do is we're going to virtualize these volumes and abstract the physical host, the physical disks, whether they are SSDs, cabins, or cloud provider disks, like such as EBS or Google persistent disks, to be able to read and write without focusing on disks that are not designed for containers, and that they don't provide services for containers. So we can create hundreds of volumes. They are cheap. They are almost free to the system until we need to use them. So when we flow input-output operations, then we're going to start using them. But it doesn't have any load to have hundreds of those volumes in the cluster. We provide capacity, and it's completely internal to the system, to access data through the network, because we're going to replicate, if the user decides to, we're going to replicate across different nodes. We are also capable to flow data across nodes. So in case of having to access data on different nodes, we don't have to follow. Ondat doesn't have to follow the data to the application, but can access remotely. The capacity that we are taking from a pool of aggregated gigabytes or terabytes, depending on every cluster. So we take every single host. For instance, here we can have 4 hosts, and every single host has 1 terabyte of data or capacity. At that point, we have 4 terabytes of an aggregated pool that we can use to provision persistent volumes. Now, what happens in the node itself? So once we have a virtual volume and it's used by a database, what happens inside that host, that whether it's a virtual machine or on-premises server, I mean. So what happens there? Well, we're going to use a front-end presentation that is a standard Linux device that we use an open source Linux, it's called the Linux IO library. So it's an open source library to register devices. From there, Ondat takes every single input-output operation that happens to this disk, for instance, coming right from an application, and we can decide what to do. So for instance, we can send the data to the local disk, and we can send the data to the replica. All of that is with our own self-implemented protocols, and those protocols are designed for the highest performance. So we have our own binary format to write to disk, and our own binary synchronous protocol to make sure that we are really fast on sending data across the network. So once this block of data is sent, we can control exactly how we do things to maximize performance. Now, one of the biggest key points is giving developers and giving operators the capacity to focus on the things that they need to do rather than focusing on things that a machine can do. So high availability is, I would say, the most basic and important functionality for anyone that wants a production-grade system when it comes to storage, but doesn't want to worry about it. So it can focus on application, it can focus on development, it can focus on things that really actually matter to the business case. So how we implement high availability is through synchronous replication. So that control plane, that brain, is capable to define 2 instances of data. And when the data is written to them, we send synchronously that data to the replica. And when we have, in this case, written to 2 different places, we will give the acknowledge to the file system. And that means that in case of failure, for instance, the second node goes down, there is a power outage, there is a termination of a node or whatever, automatically that replica becomes the primary volume, is in a matter of milliseconds, I could say even less than milliseconds, we can fail over. And because we're using a declarative model, we are already provisioning a new replica. Obviously, if we have a lot of data and we have a volume, for instance, that is 300 gigabytes, that will take a while. In the meantime, we can read and write to the persistent volume, what we call the primary. However, if the node that went down comes back up, we have a differential algorithm that is capable to resync only the data that is missing. And when that happens, we are minimizing traffic and we are improving the capacity to recover and not run on degraded performance. On high availability, we can go one step further. We can make better placement decisions based on things like topology. So we implement a topology-aware placement that allows the user to define where certain nodes are located and to make sure that different instances of the same data are scattered across different availability zones. So in case of failure, we can make sure, and we are certain, that the data is actually replicated on a different failure domain. So this is great, but actually the fact that we're running on Kubernetes and that we are using kube native primitives gives us the capacity to evolve storage services. How? Well, for some applications or for some clusters, we want a set of machines that are all the same, easy to install, fast, and that they're all the same. In that case, we use HyperConverged topology. That is the default mode, and it's as simple as we're going to place data in the same nodes where we run applications. Why? Low latency. Aside of being simple, it also gives us the capacity to run applications really close to its data. So if I have things like Postgres or Elasticsearches or Kafkas that require high throughput, I'm going to use the capacity of this storage platform to have the highest performance possible to avoid going through the network too much. On the other hand, sometimes it happens that you want centralized storage. Why? Because you can have specific disks that are faster, or there are a set of nodes that are, for instance, in an autoscaling group. And you don't want really data on autoscaling groups to avoid, losing data. So what you can do is define at execution time, and it's completely transparent, where you're going to place data and just set which nodes are going to store data. However, we give the capacity to run the applications anywhere in the cluster. Therefore, we're going to handle the network traffic with our own binary protocol to be as fast as possible. Obviously, there is network latency, but that's up to your decision. What can you take as a risk and a performance impact? So we've been talking about regret one's volumes mostly. However, given a community ask, let's put it this way, we developed regret many volumes. So this came straight from requests because some customers, they had the use case of migrating stateful applications to Kubernetes and running them in a high throughput and low latency. However, there are some applications that, whether they are legacy or they are, for instance, web applications that require access to the same file system on different instances of the application, it requires access to shared file systems. So we implemented this solution that uses the regret once volumes that we've been talking about and all their functionality to provide a layer on top that allows different containers to access the same data at the same time. There are obvious implications, but it's a solution that fulfills a lot of use cases. There are a myriad of functionality that we can go in detail, but finally, I would like to talk about encryption. Encryption is a functionality that is very important for some customers. Mainly, the way it works is we're gonna make sure that there is no data, whether it's in flight or at rest, that is not ciphered. For that, we generate keys. Ondat does that for you. So you don't have to generate keys. We will generate them per volume, and that key is generated based on different materials such namespace keys, etc. So we leverage Kubernetes objects, secrets, and things like that to create different areas of the material. Once that key is created, we can provision a volume, and that volume has no data available that is not ciphered. That key can be stored, or actually is automatically stored in etcd. However, we have the KMS provider plugin that will make sure that none of this data is visible. Probably you already know that etcd in Kubernetes is not ciphered by default. It's base 64 mostly, which makes it not secure. However, with the KMS plugin, we can achieve that security.
I have a question regarding actually the backend storage. Mm-hmm. Is it possible to specify more than one storage type backing a volume and do some kind of intelligent data tiering with your solution. Let's say I have, I don't know, a pretty large number of files sitting on what would effectively be a file share. Some are accessed all the time, some after 30 days, they kind of fall off. Can your solution tier that data across different physical media so I can pay less for the files that are accessed less often?
Mm-hmm. So the physical media is controlled by the user. So we are trying to be as agnostic as possible. So you run the same solution, the same automations, whether you're on Amazon, whether you're on Google Cloud, on VMware, or wherever. To achieve that, we let the users define their media. We let the users use different LUNs, actually different hard disks that go specifically to the Ondat container. And that is what the technology uses to write data. So if there are different kind of media that are attached to it, that is something that the user controls. There is no functionality explicitly to say, I want to write this volume into that specific physical disk. That's something that we have had as feedback. And this is something that is going through our own pipeline of requests, because it's interesting as having affinity for kinds of disks or kind of media for different kinds of volumes. However, this is not implemented at the moment. We let the users plug what they decide, even though we try to let a homogeneous layer in terms of the backend disks.
How do you manage the mapping of storage classes with the volumes in the backend, so the storage in the backend, and the physical storage? So do you have any mechanism to say this is very fast storage, this is medium level kind of storage, this is capacity storage, and then you provide volumes by building with the storage classes in mind?
Mm-hmm. So we use the storage classes to enable a certain kind of functionality. For instance, replication is something we can enable at storage class. So when you say, I want a production grade storage class or a developer one, you can define different functionality on there. However, this comes to the same affinity functionality when it comes to specific media to specific volumes. So I think, well, if I understood properly, what you're saying is, can I differentiate different media for different volumes? And the answer is the same. This is something that we have requests for, and this is something it passed through our own feedback process, which comes to the same functionality to be able to define affinity in between volumes and disks and physical disks, actually.
My question is, so you said you're trying to be as agnostic as possible in regards to what storage is underneath of it. I've noticed that SSDs and SAN is up there as well. Many a vendor or sysadmin has died on the cross of trying to go as cheap and deep as possible. Do you guys provide guardrails as to what being as agnostic as possible is there? Are there, an HCL? Is there something along those lines of really don't try this?
In the end, we're going to guide, or the technology is going to guide wherever is possible to guide. So if the user decides to bring the fastest SSD on the market, we're going to use that. But if the user decides to use something that is far from ideal, we're going to guide there. The impact is going to be in performance or availability, obviously. Availability, not that so much because we implement the availability ourselves. But obviously, we cannot guide fast. We will not. That being said, I could avoid as much as possible, as a recommendation, network disks that have high latency. And those network disks, usually on cloud providers, are fine. Obviously, there is performance implications. What I could avoid more than anything is using shared file systems on the backend. Shared file systems are not great at handling a lot of input-output operations. So the IOPS for shared file systems are usually quite horrible. For big files, sometimes it's fine, but in general, it's a bad idea. So I would say that we try to be agnostic, but also it depends on the hardware that people have. And we don't have to be specific, and we don't have a big requirement on hardware to run. You have faster hardware, you're going to run faster. You have slower hardware, yeah, you're going to have an impact. But we're not going to restrict you on that, if that makes sense.
Well, I mean, yeah, it does. But performance is definitely an aspect of this question, but then you get into things that are like byproducts of bad performance, durability of the data, corruption, things along those lines. Like I said, never underestimate the capability of a sysadmin to do very crazy things with their storage, and you have to kind of protect against that. Is there any, like I said, is there any kind of protections there? Because I mean, it's kind of like a roll your own, do what you want.
This is a question that does come up quite often. The simple answer is, we've optimized the data plane, we've optimized the technology to be able to make the best use of the different types of systems. But in terms of compatibility, and things like having a hardware compatibility matrix or having specific versions of firmware or whatever else is largely down to whatever Linux supports, right? So if the vendor that you're using is certified for Linux and has that capability, then we can consume it. So we kind of use Linux as that layer of abstraction. We don't want to, wherever possible, we're using standard interfaces like the Linux SAS interface or the NVMe interface or whatever else to be able to access those disks, and as long as those products are certified for Linux, then we tend to be fine.
Thank you.
On top of that, I was about to go into detail, but on top of that, there is protection that to make sure that what is read from a disk is actually what we wrote. So we have an algorithm that actually checks with a high sum every single time to make sure that if the disk comes with something that actually is not what it was supposed to be, we just don't accept the read. So we will never give that to the application something that actually is not meant to be there. So any more questions?
I have another question about the optimization of the data path in the backend. So as far as as my understanding goes, I mean, you don't do any optimization in the backend. So you don't use, SPDK from Intel or things like that to optimize NVMe or anything else that could, give the best possible performance and efficiency, right? So you just use the devices as they are presented from the operating system.
Yes and no, and I'm sure Alex has a lot to say here. I could say we implement the block model that we write to disk. So we decide exactly how we write data. So it's not, we're going to use this disk and that's about it. That's a bit simplistic and it's fine for an overview, but actually we control the alignment of blocks. We control a very, very low level detail on how we write every single bit or block of data, if you will. And there are a lot of performance improvements that happen over time based on that, based on how we write data, how we read data. There is optimizations that are specific for different data models. There are some optimizations that are specific for some kind of disks. And what do I mean by this? For instance, if you have something like video, you know that you have a lot of data that is sequentially accessed. You can start prefetching data. So a lot of this kind of functionality is very deep, but there is a lot of performance enhancements based on how we access data in disk. There is also optimizations. We use certain specific instructions on the Intel chipset. We can go into detail, but yes, we do have a lot of detail of implementation that comes to a performance enhancement. And based on that, actually, the Ondat is one of the fastest, if not the fastest, technologies in the market for containers. And we've put a massive...
But we are talking about technology that is available, on top of the, of the media. You are not really managing the media. You can do it with any single type of hard drive or SSD. You don't actually think about the difference about this type of media, right? So if you're working with Optane, are you treating Optane differently than an hard drive, or do you have any specific implementation for QLC or things like that? So that I have more option to build my infrastructure, or do you limit, your customer to SSDs and that's it. I mean, enterprise grade, write intensive SSDs.
So
Alec?
just to answer that question directly, right? There is a lot of intellectual property that goes into the way we process the data and the way we write the data. And yes, there is, like for example, we create our own metadata that handles the indexing and the alignment of the blocks to make sure that they are optimized, and things like overwrites and retries, etc., happen in the right order, and also store things like checksums, etc., irrespective of what the underlying device is actually doing. So effectively, we're adding those sort of value add components irrelevant of the device underneath, and then we have a number of different optimizations to handle the placement of different workloads and things like prefetch and read ahead and optimizing the threading models and the layout and distribution of data across multiple drives to balance workload, etc. So the answer is, if you're using a hard drive, or if you're as in spinning media versus say an SSD versus an NVMe versus different types of SSD like QLC or whatever, we will in all cases do our best to minimize both read and write amplification, and we will minimize the because whether it's a data intensive transaction or whether it's a sequential workload, either way, we do always do the best to minimize those systems, and we use things like log structured file systems and log structured methods to do that. And then like Ferran said, we also use a ton of acceleration that are built into either the different kernel facilities for those NVMe drivers, or the actual CPU acceleration. So hand-tuned hashing algorithms, hand-tuned placement algorithms, hand-tuned encryption algorithms to make sure that all of those things happen as quickly as possible. And in fact, the net result is just measure the performance yourself, right? In terms of our benchmarks, we're always providing the lowest latency as a result.
As a conclusion, I would like to recap a bit on the different topics that we are following to implement this solution. So we want an application-centric model. We want Kubernetes to be able to ask, hey, I want capacity, but I don't want to care how you do it. I just want that capacity for this application because I'm an application-centric model. So I want my developer to not need to know too much about how you handle these things, just handle it. So we want a self-service system that is declarative with high performance. That is obviously a given, but you would be surprised how often happens that a lot of solutions are just not able to perform for low latency and a lot of throughput. We need scalability. And scalability means that it's as simple as adding more nodes. We horizontally scale by just adding more nodes, and everything else is handled. We have more capacity. We want more disk. Fine, we can plug more disk. It's just transparent. High availability is something we discuss at length, but I think it's fundamental to be able to run any application or any container that requires state, and to be done for you without you having to worry too much on how. There are very often providers or services that charge based on IOPS per gigabyte, usually cloud providers, because they use a model where you have disks that are designed for virtual machines. When you have a container-centric storage model, you don't have that problem anymore. So imagine in your cluster, you have hundreds of volumes. Most often than not, you will have volumes that are 50 gigs, 100 gigs, 300 gigs, but you will have a lot of them. So aggregated capacity will go maybe to 4, 5, 10 terabytes, 300 terabytes, whatever it is, but every single volume is not going to be that big. When you have IOPS per gigabyte as a model, you will have a big price increase if you need performance, because you just don't have enough capacity to make sure that the performance is actually good. So there is a big reduction cost in here. We want a system that is agnostic. So whether you are in your development laptop, or you are in a cloud provider, or you're on premises on VMware, you want the same kind of operation, the same kind of integration. You don't have to worry too much, even on hybrid solutions, worry too much and have different knowledge and different procedures for different platforms or different areas of a platform. So with one solution that is agnostic, you're capable to abstract most of those differences. And finally, we want, and we discussed that already, a secure system that by default encrypts everything on flight. So no replication data is visible, no data on disk is visible. So you keep a tight and secure system by default, by design, not as an add-on on security. So yeah, I would like to thank you. And if you want to try this, it's actually very simple, it's very smooth, and hopefully if you can help us, it's going to be even more easy. It's going to be easier and more smooth.
I'll just ask a question real quickly. Since that slide shows tech preview, is this in preview? Is this available? Can companies use this?
So it's fully available. It's been available for years. It's implemented or deployed in production in banks, or different. We have different areas of customers. The tech preview is something specific that we could disclose, but it's something that I could like to introduce, because we are implementing different areas of the product. We are implementing the product really fast. And what we do from time to time is roll out certain functionality, see how the community responds to it. And based on that, we finalize that functionality or we take that functionality. So the latest version that we have actually has a tech preview. So we are at the moment in 2.5. So we've had a long run on this. Just there are a few functionality that is at the latest tech preview. So I encourage any early adopters to start using that.
I just wanted to add something on top of the performance, because I think we spend a lot of time on individual disk performance, but I don't think in the end it will matter too much. Too much, because the way we aggregate individual disks together, it's like we are building a sort of red zero anyway. Right. So, we can go as much as we want into the details of how we optimize, but remember that we don't consider the performance of a single disk. Every time, if the more disk you add into our engine, the more performance you will have, right? Because we will read in parallel into all those blobs.
Yeah, it's very important to take into consideration not only the performance per unit, but the performance as a whole in the cluster.
Exactly.
Yeah, and I think that's a really, really good point, actually.